So tonight we're going to look at a little bit more application rather than theory, right? Our first session, we kind of got an introduction. Of course, last week we were very heavily into the calculations involving noise and so on and so forth. I want to fall back a little bit and talk about practical application, some of the stuff we've learned so far, and how you make sound level measurements and what kind of instrumentation you use and so on and so forth. Since not many of you have, I brought a sound level meter and I brought a small dosimeter. In a second, we're going to know what those instruments are, what the difference between those instruments is. But I brought a couple of small instruments that we could pass around, take a quick look at, maybe even make a measurement or two. And maybe if the fan comes on, we can, see how many decibels that are coming out of that vent over there. So I'll pass those around. We get a look at them and we get a little bit of an introduction. But since you haven't taken the lab, I'm thinking next week we tentatively have a guest lecturer on heat stress next week. He'll be doing at least part of the lecture on heat stress. It's been scheduled ahead of time. So if he is here next week, we'll do that for the first part of the lab, and then maybe we'll get into noise measurements again towards the end. Or if he isn't, we'll just do all noise next week. We'll finish up with noise next week. And what I'll do is I'll bring in a speaker, make some white noise, some pink noise, and we'll actually maybe play around with some measurements, take a look at some of the things that we've been talking about. In other words, the effect of an enclosure, the effect of distance from the source, and so on and so forth, how it attenuates the sound, and so on. How we might do a measurement of the sound pressure levels at different distances from the source, so that we can kind of map out the sound levels as if we were doing an investigation. So it'll give us a chance to actually do a little bit of hands-on stuff, even though this is not technically a lab. It'll really help you kind of cement this whole thing. Okay, so one of the things we're interested in is how to calculate the dose at the sound pressure level, the actual level of noise that is present at the point where the worker might be, and also to calculate the worker's dose. In other words, how much noise is he really getting exposed to? And of course, the dose is not just the intensity of the sound at that's given moment. It's a combination of the sound pressure level and what the length of the duration is. Just like a toxin, right? It's like, how much is in the air and how much time he's exposed to it and so on. So we'll take a look at that, because I think that's important to know about. That's something that you might actually apply. Okay, we'll talk about what's the appropriate measuring devices, what the differences are between them. And we'll talk about hearing protection. You might have noticed I brought in a helmet with hearing muffs, and I think I have enough earplugs to be able to pass them out, so we can play around with them and talk about the proper way to it. How many of you have ever been trained on the proper way to put in earplugs? Okay, how come? Where were you trained?
You're exposed to noise.
Yeah, and what you were working in a noisy environment, or as part of a OSHA course? Or?
No, so for the previous company that I worked for,
yeah, there you
there
go.
was a potential doing environmental remediation project,
right,
to be exposed to noise, so we were taught.
Okay, good. All right, there you go. Okay, let's talk about noise measurements. Okay, here's a random bunch of instruments here that we're going to be talking about in a second. In addition to instruments that we use to measure sound pressure levels and measure dose, we also, of course, have to have devices that allow us to calibrate those instruments. A measurement is never any good unless you can rely on it to be accurate, right? So in industrial hygiene, we're always calibrating. Everything we do, we calibrate. Okay, if you do occupational exposures, you're going to want to calibrate all of your instrumentation before you do the exposure measurements. You want to calibrate them again after you do the exposure measurements. So, and if you're involved in any litigation, one of the things that's going to come off if you have expert testimony is they're going to ask you, did you calibrate the instrument? What method did you calibrate the instrument? What does the manufacturer say about how to calibrate it, and so on and so forth. So if you really get involved in sound level measurements, and there could be any kind of litigation involved, you want to make sure you're calibrating correctly. Yeah.
Is there a way to maximize the screen?
You mean make it bigger?
Yeah.
Okay, let's see what I can do. I think I can. That's a little better, eh? Okay, that's about the best I can do.
After the title was cut off.
Yeah. Is it? Oh, I see what you're saying. Yeah. Okay. Okay. So sound level meters. This measures the sound pressure variations in the air. That's your SPL, your sound pressure level, your micropascals, and so on and so forth. Okay. It provides basically instantaneous readings. That's not really true. It actually reads over a short period of time, from milliseconds up to, say, a full second. In fact, most of these instruments have a setting on them for a fast response or a slow response. When you're doing very sophisticated laboratory work, you may need to have a very fast response if there's a very short duration sound or something like that. But for most of our measurements, we're going to use a slow response, which updates every second. It averages readings over a second, roughly a second, and it displays the reading that for that average for a second. It's you'll see the numbers change like every second or two. The fast responses, they're just dancing through the instruments. Very hard to get a reading on. Oops. Okay. Okay. One of the things that we're going to use a sound level measurement device in this this SLM for is, since we can just carry it around the room and read sound pressure levels, we can use it to do surveys. So for instance, in this case, what's happening here is there is a 92 decibel source over here, a filling machine, there's a high-speed blender over here, 98 decibels, and so on and so forth. And what they've done is they have used this sound level meter. They've used this to take a radius of 3 feet, 6 feet, and 8 feet around, and they've measured how many decibels of sound, how much noise. They've measured each one of these areas. So if you're outside of this area, right, and people that work outside of this area are exposed to less than permissible exposure. They don't have to have a hearing protection program. If you're inside of that line, you have to have a hearing protection program. And you can take a look at how you get combinations of. In this case, what they're doing is that they're not necessarily they're measuring and where they have a 90 decibel sound level, and then where they have an 85 decibel sound level, and 80 decibel. So you can almost like a barometric chart. You can actually construct. Yeah.
Are those radii just one measurement, and then you?
No, many measurements. No,
you do a lot. So
yeah.
At three feet.
Yeah, exactly. Exactly. You would have many of them. And in fact, really, in most situations where you're doing a real sound survey, what you're doing is that you might take a 3-foot diameter. You might actually take a sound level reading here, and where it measures 90 decibels, make a little tick mark there. Then move over here where it measures 90 decibels, make a little tick mark here, 90 decibels, 90 decibels, 90 decibels, 90 decibels, and then connect them together. So it's kind of like, from that point forward, you're about 90 decibels. And similarly here, they might do with 85 decibels, and they might do with 80 decibels, and so on. Okay, so in this case, this is a sketch Brian made up. In this case, he's actually just, measuring he's measuring 8 foot from that source, and he's measuring it in a couple of spots, and it's averaging about 85. But in a real sound level, these would not be nice concentric circles here. They might be wavy and stuff like that, because you want to see the points at which you exceed a certain level. Okay, spot checking noise, spot checking the levels of noise that are present, and also checking the levels an inch of noise that are measured by a dosimeter. Vicinity of his head. Basically, when you take sound level measurements, you're considering basically a 2-foot sphere around a person's head. So you would have an instrument or a microphone that might be on his collar or on a device that he's wearing on his head or something like that. So you can take sound level measurements right in his hearing environment. Okay, so that dosimeter, that's what OSHA wants to know about. That's what's going to determine whether or not you have you require a hearing protection program. Okay, so whenever you're talking about OSHA permissible exposure levels, you're always talking about specific measurements on the worker, right? So you're not talking about area measurements. So in this case, you might use this as a method to check that dosimeter to see if that dosimeter is reading properly. Okay, and we'll take a look at what the difference looks like from these two things. To check a worker's noise dose whenever a dosimeter is not available. So you can take maybe a quick reading to get an idea of whether what the measurement is. Again, the only thing that OSHA is concerned about is 8-hour time-weighted exposure for determining whether there's a permissible exposure limit. So you can take a short-term measurement to get a rough idea, and maybe you have a high level of confidence that it's always going to be below that level, and you decide not to do individual monitoring. But if it's anywhere near close, the only thing that counts is individual monitoring. Also for evaluating individual noise sources to decide which ones you have to control. In other words, in the work area, if this is making a lot of noise and this one is tolerable, you might be able to figure out ways to move them around or locate them and so on and so forth. To kind of engineer the area so that you don't have areas that exceed the permissible exposure limit. Aid in engineering controls, and so on and so forth, to decide which ones need enclosures and so on. So it's basically like a survey device for the most part. Yes. Oh, you got both. And dosimeter means anything that measures the dose that work is exposed to, right? So it could be a radiation dose, could be a noise dose, could be if there were, in fact, they have carbon monoxide devices where you can wear, if you work in the carbon monoxide environment, you can wear a badge that changes color, right, as you're exposed to carbon monoxide. So if you wear that over an 8-hour period, you can, at the end of the day, hold it up against a chart, and you can, see what your dose was. If I have a device to measure carbon monoxide in my hand, a direct reading device like an IIQ and/or air quality monitor, and I can read on there an instantaneous reading what the level of carbon monoxide is, that's not my dose. That's just the current level, right? The dose is what you've been exposed to while you've been in that environment, right? So, and it's time weighted, right, over that period. Let me, since we seem to be talking about this so much already, somebody stole my table. How did the table? What's that? Oh, it's back there. Okay. All right. Okay, here's a sound level meter. Okay, this particular sound level meter can be programmed for A scale, C scale, and Z scale. It's currently programmed for A scale. You'll see it on here. It'll say LAS. L is for sound pressure level, and AS. And right now, as I'm talking, it's reading about 70 decibels, 75 decibels. So if I want to start doing a survey in here, what's the first thing I have to do with this thing? Bingo. Thank you very much. Okay, excellent. I have to calibrate the thing. Okay? So we have devices for calibration. This basically is a little sound production device. If you read somewhere on it, right down here, it says that it produces 114 decibels at 1,000 hertz. So when I turn this switch on, can you guys hear that from back there? Right, when I turn the switch on, you can actually hear this making noise. Okay, so now I'm not measuring this out here. I actually have to put this in here. And I got the wrong one for this particular device. Notice the hole is too small. They have inserts for them, right? So in other words, for a different device, for this device really should have a different insert. But I can, in the meantime, kind of hold it like this. What's it read? 108? Yeah, why is it not 114? Because it's not enclosed. It's not, in other words, it would normally be completely enclosed. It would just barely slide in here. And it would actually read 114. This instrument I know is calibrated, right? So if I had the right sleeve for it, it would read 114. So now I know that this thing is, at 1,000 hertz, is reading properly. Okay, and so I could also now find the sound source. Next week, I was going to just hand this around. Next week, I'll bring in a small speaker so it can actually make some noise. Okay, one of the things I can do with a small speaker is I can generate a sound that basically is equal. It's an equal loudness, equal sound pressure levels in all of the frequencies, low frequencies to high frequencies. Anybody know what that kind of sound is? A lot of people use it to go to sleep at night. White noise, exactly. White noise means that all across the bandwidth from 20 hertz up to 20,000 hertz, it's the same level of energy that it's producing. So that's white noise. How about pink noise? What do you think that might be? All right, well, pink noise, I'm going to take a wild guess at this. Pink noise has more energy in the higher frequencies than it has in the lower noise. You actually hear the difference, but at some point, maybe next week when I have a little speaker here, I can put my iPhone on it and play the two different kinds of noise and measure. Let's say that I have white noise and I'm producing white noise. And I put this instrument on the A scale. That simulates the exposure to the human, the effect, the health effect that you would have on the human for that type of sound. Okay, so we're on the A scale. If I use the Z scale, it measures all the frequencies equally. And so it's going to measure all of the frequencies in the white noise. If I put it on the A scale, it's going to attenuate the lowest frequencies and a little bit on the highest frequencies also. Which one is going to read higher, the A scale or the C scale? What do you think? Right? Which one's measuring all the energy? The C scale. C scale's going to read a little bit higher, right? I'm not going to be able to measure, what frequencies are going to be higher, but it's going to measure a little bit higher because it's not going to attenuate those. It's going to measure everything together. The A scale is going to discount the lower frequencies, higher frequencies, because our ears are not as sensitive to that. We're not, when we're exposed to it, we have fewer receptors for that, so we don't have to be quite as concerned about that in terms of exposure. So I'm going to pass this around. You can talk into it, sing into it, Strangers in the Night if you want, or something like that. Give it a try. Nobody sings Strangers in the Night. I don't remember the last time I heard that song. I gotta get the truth. You don't hear much Frank anymore. Ever since he's been dead, he's forgotten. Actually, I hear Nancy Sinatra more often than I hear Frank Sinatra. Excuse me? We're going to talk about that in a second. Type 1, Type 2, and Type 3. The most accurate of these instruments is a Type 1. They're super expensive. You'd only really use them in laboratories. So for instance, for calibrating other instrumentation, for testing sound protection devices and so on and so forth, for determining what the noise reduction rating is on a product like earmuffs or something like that, you would use them in a laboratory. Type 2 are more general use, right? They're very accurate. They're pretty expensive, but you might use them for field measurements and so on and so forth. And Type 3 is the least expensive of those. And I'll tell you what, for next week, I'll send out an announcement. Why don't you guys download a sound level measuring app on your phones, right? So that way we can all take some readings, see how well these things work. If you can find one that's both sound level measurement and dosimeter, that would be great. If not, don't worry. Don't spend money on it. Just find whatever seems to be the most popular free version for your phone. What's that? Yeah, NIOSH has one, right? Yeah, give that a try. Somebody give that a try. Yes. 0, 1, 2. I thought it was 1, 2, 3. Let's see. I'm frozen.
The slide up there says 0.
Yeah, slide says 0. Type 1, Type 2. Yeah, it said Type 0, Type 1, Type 2. Yep. You're right. Seeing your moment. Cost and performance vary with type, of course. Okay. So basically you're looking, the difference is really the accuracy of the various devices. Survey grade Type 2 is the least expensive. Engineering grade Type 1. And you'd see them in the field quite a bit. Type 0, you'd almost never see in the field. I would guess that's probably, let me see, that thing over there, probably guessing based on what it's cost, I would say it's probably a Type 1, I think, plus or minus 1 decibel. If somebody goes online, they can look up the specs for it and just look up what the or the accuracy, it's plus or minus. Yeah, it's on there. What's that? It's a type 2. Does it say on there? Yeah. Okay, so it's plus or minus 2 decibels. But that's basically how you would know which one it is. Cost, accuracy, cost, and which is the accuracy is a lot of it is determined by the quality of the microphone. Okay, type 1 versus type 2. What do we got in price there? 1,300 versus type 1 is 3,000, and that's 1,300. I think the price is much cheaper nowadays than they were then. Okay, so how do we use this thing? First, you position the microphone in the worker's hearing zone. If you want to make a quick measurement, a short-term measurement in the worker's hearing zone, again, that's like 2-foot circle diameter around his head. And then you measure. You want to hold it 1 meter. You want to hold it out. You don't want to hold it close to your body because your body is going to be attenuating some of the noise that might be produced. And you want to use a windscreen because you don't want to get measure short-term change. Remember, the wind, the pressure of the wind, right, is much greater than that little bit of pressure from the sound. So it can really impact the reading that you get. So literally, that is much greater than what my voice is. My voice doesn't produce that same effect on there. Okay, so slow response. Again, you're in the millisecond range for fast response. You're in the second range for slow response. And typically, we'd be taking readings at slow response. Now, dosimeters. This is the dosimeter. Has a little clock in it as well as being a sound level measurement device. And it will give you sound level measurements. Okay, let's turn it on. Okay.
Sound level meters are not capable of calculating
No, because they don't have that. You can program them to store. Some of them have memory in them. You can program them to store data, which you can download to. Many of them have programs you can connect to. You can download the data, maybe take a reading every minute. And from that, when you download it, either you can do it on your own, like with Excel, or you can use a program that it comes with to calculate the dose that they were exposed to. Okay. But they themselves will not display it. Now, a dosimeter actually has everything. It's a little computer in there. It has everything you need, not just take a sound level, short-term sound level measurement, but also to calculate the dose, the percentage of the permissible exposure limit that you were exposed to. Now, given this instrument has a lot of different settings on it, I have it set up so it's reading. It's right now 71, but I read about the same thing, about 70 decibels as we saw before. I might hold them. One thing we might want to do is hold these two together, the sound level meter and this together, just to do kind of a quick bump check on this thing. So what are the settings that I want to put this on if I'm going to do worker exposures? First of all, what's the first thing I want to do? What's that?
Make sure your battery's full.
Yeah, make sure the battery's full. How about calibrate again, right? The calibrate is the first thing we want to do. Second, make sure the battery's full. How about the third thing? What setting? Okay, we want to tell it, we want to program it. So if we're not there, we might have it just reading continuously. If we're going to be on the job site, it's going to wear it for the full 8 hours. And we can talk about later on what the idea of whether you should wear it during breaks and stuff like that and so on. Okay, most people leave on during breaks because it's just more practical. But what are the variables here? When we measure sound, we have a couple of things we have to be concerned about, right? In terms of like what we're measuring. Okay, so if we're taking measurements of the human exposure, what setting do we have to have on here? A scale. We want to make sure it's on the A scale, right? Probably want a slow response. And there is another thing in here, and that is that OSHA has really 2 standards for exposure to noise. It has its permissible exposure limit, right? it also has another version that's called a hearing conservation standard. Remember when we talked about the OSHA permissible exposure limit? What's the problem with that exposure limit? It's one of those exposure limits that are not protective. If you're exposed at that permissible exposure limit, after 20 years of exposure, you're going to have significant hearing loss, right? So it's not a protective standard. So employers have the option, or unions have the option of enforcing a more rigid standard, right? So you have a hearing conservation standard for OSHA. Who else has a standard for noise exposure? NIOSH, right? NIOSH has a recommended exposure limit, right? And they have their own method of calculating, right? And how about anybody else? I think ACGIH has one also, but I don't think anybody actually uses it. Right? And I think it's pretty much the same as the NIOSH standard. So let's pass this around. Yes. I'm sorry, ANSI? That's probably the same as the NIOSH, but that'd be my guess. But my guess is they probably would have something, But again, the big ones that are used are the OSHA permissible exposure limit and the NIOSH recommended exposure limit. And it's also going to impact how we do calculations in terms of if we don't have a dosimeter, if we're measuring sound levels differently, how we're going to determine what the exposure is. So if we have to do it kind of manually. You guys want to pass this around? Hold them side by side. Read them first and then talk. So? Are they close? So, okay, it's pretty close. They're within a couple of decibels of each other, right? Which makes sense. What did we say the accuracy was on that type 2 meter? Plus or minus? 2 decibels. 2 decibels is a lot of sound, right? Remember, it's a logarithmic scale. So 2 decibels is a pretty significant difference. That's why the laboratory grade one, which is much more accurate, is used for a lot of important kinds of calibrations and measurements. Okay.
For the other instrument, I blew air into it without making any sound.
I'm sorry, say again?
I blew air into the other instrument.
Yeah.
Without making any sound. This was measured by 20.
Yeah, it bumped up. That's why you'll notice on the dosimeter, it has a windshield on it, right? And you should probably have the windshield on the sound level measure. See where I got it.
Industrial environment, we have to
Yeah, pretty much. I mean, if you're indoors and there's no air movement, stuff like that, and you're alone, there's not a lot of activity, you wouldn't bother with it probably. But if you're outdoors or if you're in an environment where there's a lot of motion and activity that generates air currents and stuff like that, you would put like that. Yeah, this on. Who's got it right now? Well, you're supposed to catch it. Yeah. All right. So yeah, put the windshield on it as you're working with it. And if you want, you can pass this around. Okay, and don't stick this in your ear when you turn it on. Do me a favor. Don't laugh. It happens. Get it away from me. It's annoying. Yeah. That's, you can't change the volume, right? Because the volume is, a standard. Yes.
How often do you calibrate that?
I would say if you're doing field measurements or if you're doing worker exposure, you want to calibrate it before and after you use it. Every time you use it, basically. Okay. So dosimeters. Typically, for permissible exposure limit, you're typically working for an typical 8-hour workplace exposure. Okay. You want to record other environmental characteristics, your temperature, humidity, and so on and so forth. Need to be pre and post calibrated, as I said, before and after you use it. Okay. Okay. So the dosimeter is the primary instrument for making compliance measurements. Why is it the primary? I mentioned this already, but I want to emphasize it. Why is the dosimeter the primary compliance device for OSHA as opposed to the sound level meter? Why is that one the primary instrument? It's attached to the worker. It's measuring his exposure during that entire period of time that he's working. The other device is just taking short-term readings. Okay, so that's why it's primary. Okay, OSHA criteria, and the way that this, if this is set up for the OSHA PEL, it has a 5 decibel exchange rate. We're going to get into a chart in a second where it discusses the level of sound exposure and this thing called exchange rate. So if you are exposed to noise at work that's over 85 decibels, what happens? What do we apply? We have a hearing conservation standard. What does that mean? What do you do when you have a hearing conservation standard? We spoke about this briefly, I think, last week, right? What does that mean? So now you're exposed to too much work, more than the OSHA standard, which is 85. Does it mean that you have to start wearing earplugs and earmuffs and so on and so forth at 86 decibels? No, because the permissible exposure limit at 8-hour time weighted is 90 decibels. 85 is where the standard kicks in. At that point, you have to evaluate the worker's environment, decide whether you can control it below that, and among other things, you have to provide education, and you have to monitor the worker's hearing during the course of his career, during the course of his work. Okay, so those standards start to kick in. The actual exposure limit for OSHA is 90. For NIOSH, it's 85. For OSHA, it's 90. Okay, so now that means you can be exposed for how long in a workday at 90 decibels, right? Was OSHA standard always 8 hours, right? So you can be exposed to 90 decibels for 8 hours. Well, now, what if you're exposed to 95 decibels? What happens then? Can you be exposed for 8 hours? No, you can't, right? Because you'll only be exposed to 90 decibels for 8 hours. OSHA uses an exchange rate of 5 decibels. That means for every 5 decibels you go up above 90 decibels, you can only be exposed for half of that time. So you can be exposed at 95 decibels for 4 hours. How about 100 decibels? 2 hours. How about 105 decibels? 1 hour. How about 110 decibels? Right, half an hour. So every 5 decibels cuts the exposure time in half. Okay, so that's a 5 decibel exposure limit. Does NIOSH use a 5 decibel exposure limit? Well, we're going to find out. We're going to come across OSHA pretty soon. And the type of reading you're going to take is a slow measurement. And at 85 decibels, you have the hearing conservation program, or 90 decibels, you actually start to put in administrative and engineering controls. Administrative controls means we're going to talk about that. We got a pyramid that we're going to come across in a second. I'm getting ahead of myself. Okay. Okay, so what are the issues with dosimeters? Well, one of the things that you can have a problem with is when they say contamination, they mean very short duration noises that are very intense. So for instance, if every once in a while there's like a very loud bang or something like that, it can make it more difficult to figure out what the level that you're continuously exposed to, right? The other problem is that if you start the sampling before you actually put it on the worker, right? You can throw the readings off because you're manipulating the thing and so on and so forth. So you want to start the sampling after you place the mic on the worker. And you also want to make sure occasionally that it's actually reading correctly by taking sound level measurements and making sure that they work together, that they're agreeing with your dosimeter. Like we just did here. We compared the sound level meter with the dosimeter to see if they were reading similarly. Now, octave band analyzer. Let's see if I can't have a, if I have a, okay. So, in some situations, this is not necessarily in most measurements where we're trying to comply with the OSHA standard. In some situations, we may have devices that produce noise that's predominantly in certain frequencies, right? And we may be able to use special devices to protect the worker from those frequencies that are better at filtering those frequencies out, or we may be able to alter the instrument or enclose the instrument to find some way to attenuate those particular frequencies. But in order to do that, we have to know what those frequencies are, right? So there are versions of those sound level meters like this that are also active band analyzer, octave band analyzer. What's an octave? Anybody on the piano, what's an octave? Anybody know what the frequency of middle C is? Huh? I think it's and somebody was playing the piano, right? I think it's 800, what is it, 440, 880? Huh? That's A? Say, I knew somebody would know. What is C? You know? Okay, we use A. That's middle A is what, 440? Okay. What's the next octave up? What's the frequency of the next octave up? It's easy. Double it. It's 880. What's the next A? Right? 1720, 1760, right? So an octave actually doubles the frequency. And it's broken up into how many steps? Octave. 8 steps, with like keys in between, half steps as well. The keys in between. So when you play a piano and you hit low C and you hit high C, they resonate, right? Because one is double the frequency of the other. So they line up every other way it lines up. So and you can hear that, right? That when you tune, like when people tune stuff, right? They're looking for that quiver, right? They want to get rid of that quiver when the two notes are just a little bit different, so that they actually resonate. So somebody bring in a guitar next week so we can actually see how that works. We'll take if we have combined an active band analyzer, give it a try. So now you know that middle A is 440. Each octave is double is a range that starts at a certain frequency and is up to double that frequency. So if you look at this, here are a series of octaves from 22 to 44 hertz, right? That's one octave. From 44 to 88 hertz, okay? And the number that's in the middle there is kind of a weighted average of the energy that's in that whole octave. So there's a little bit more energy in the higher frequencies than the lower frequencies. So it actually kind of leans up. It's not right in the middle. It leans up a little bit. So when you look at an octave band analyzer, you may not see 22 to 44 hertz as the lowest band, right, in the lowest octave. What you'll see is the midpoint, 31.5. And the next one is 63, but it's really a range around 63. Next one's 125. So we can take an octave band analyzer and we can tell it to measure the sound pressure for only the band that's around 125 hertz. And then only the band that's 250 hertz. And only the band that's around 500 hertz. So we can measure how much energy there is at each one of these octaves, okay, as we go up. And if we, in certain situations, if it's white noise, what are we going to find about the energy in each one of these octaves? It's going to be flat. It's going to be flat. Okay, but if it's a normal noise where you have a machine that whines or something like that, very high frequency, you almost know right away that the highest energy levels are going to be at the highest frequencies, not at the lower frequency. And you can actually have some of them that you can actually show graphically what the octave, where the energy is in that noise that's being produced. When we had an octave band analyzer before, I would set up a speaker, generate white noise from the speaker, and we would set up the octave band analyzer to measure it. And it would work pretty good it was pretty good at measuring almost exactly the same level at, say, from 125 decibels band center up to about maybe 8,000 band center. And then, it was close, but it wasn't really the same, even though it was a white noise at either end. Anybody got any idea why? Right? I mean, the program in here generated a perfect white noise. What's the problem? Why wasn't and the instrument was working right, why wasn't I reading exactly the same energy in every bandwidth, especially not the furthest ones from the center? Anyone want to guess? How many of you guys have ever bought a high-end speaker? Right. Do you get a chart with that high-end speaker? It's got a graph. It's kind of like a graph, and it has like this thing that looks like something like that. It goes flat, and then there's a little bend at the beginning and at the end. Yeah, exactly. What you're getting with that speaker is you're getting a demonstration of what the accuracy response of that speaker is. You know, back in the days when you used to go to Lafayette Radio and Harman Kardon on what's that, 47th Street, whatever, all these high-end speaker makers, you would get a chart like that. And the chart would tell you if you put in exactly the right amount of energy, you know, exactly same amount of energy into all this and the real white noise, you put it in that speaker, this is what you would get out of the speaker. None of them were ever flat lines. The closer to a flat line, the better the reproduction of sound is. But they never do. So even if I put a speaker in here with white noise on it, right, it would be predominantly white noise, but really at the far ends, right, that speaker wouldn't have to perform, wouldn't be capable of delivering exactly, recreating that exact white noise. So it's almost perfect white noise, but not quite, because this is okay. The program can produce it, but the speaker can't deliver that way, right? And we can use an octave band analyzer to check how good a speaker is at producing the exact sound that we want out of this thing. Well, why would you be interested in that speaker, right? What do you want that speaker to do? If you have Itzhak Perlman playing the violin, right? You want that speaker to spit out exactly the same sound that you would hear if he was standing in front of you. Is it capable of doing that? Almost, right? A speaker that has a very perfect flat line would literally do that. Right? It would reproduce the sound that went in exactly the same way. But it's really, in reality speaking, you know, like very high-end ones do it pretty well, but none of them do it perfectly. So that's one of the reasons you might be interested in a laboratory of being able to take active band readings is to see how efficient a speaker is, how sound production devices respond, and so on and so forth. Occupationally, we might be interested in it because it might impact what kind of hearing protection devices we use and what kind of control methods we might use to reduce the sound exposure, right? So occasionally you might be able to use it. New York City, 20 or 30 years ago, if you called up the Department of Health, made a noise complaint. I used to live on 91st Street, 2nd Avenue, across from Rupert Knickerbocker Towers, right in a tenement building. This is going back into like the late 70s, early 80s. And there was a bar on the first floor called Home. Anybody know the place? It's not. Okay. The bar, it was a famous bar. It was like, you know, with like Lennon, John Lennon had like owned an interest in it or something like that. But at any rate, it was a bar. So they would have music all the time. And, you know, I was young enough that, you know, it didn't bother me, but there were people who complained if they played late and stuff like that. So what would you do? If you didn't like it, you call up the New York City Department of Health, make a noise complaint. They would send someone down. That person would go to your apartment with an octave band analyzer. The law at that time had different, in other words, because you guys know that anytime you've been on the highway and somebody's pulled up to you and they have the radio set real loud, but you got your windows up, they got their windows up also, you hear the sound, but you don't really hear the words, all right? What do you hear? What part of the octave band what part of the sound do you hear? The high frequencies or the low frequencies? You hear the low frequencies, right? You feel the vibration, you hear the low frequencies and stuff, it carries, right? So the theory was that they would measure all these different frequencies to decide whether, what point it's annoying enough that you have a case, right? So they would actually send, the guy would have to go up to your apartment in the middle of the night or 1 in the morning when I don't know, some punk group was playing at home, and measure at your window, take measurements with octave band analyzer, record it all, and so on and so forth. It became so common, then they have to go to court with all the paperwork and the documents and so on and so forth, and try to explain to the judge what an octave band analyzer was. So that's, you know, you can imagine what that was like. So eventually they've given them up. So how does the New York City Department of Health respond to noise complaints now? Anybody know? Well, that too, yeah, they do. They start with that. If the complaints continue, they actually send somebody up there. But how do they measure it? How do they measure it? Well, now, according to the health code, they go up there. The guy opens the window. If it sounds too loud, he says it's a valid complaint. They make a judgment. Why? Because it's so cumbersome to do these measurements, and then in court it's very difficult to demonstrate what they mean and stuff like that. So, but I mean, there's reasons why we might be interested in that, and so on and so forth. Now, sampling during breaks, for the most part, I think most people leave the in place during breaks, you have to make a judgment, because if the break area is noisier than the work area, if the 8-hour period is included in the work day, in other words, the guy really works 7 hours and he has an hour for lunch, you might want to consider, taking that reading. But if he works 8 hours and he has an 8-hour break, well, in that case, you don't want to include it, because you only want 8-hour exposure, right? So you have to make a judgment. Okay, and like for instance, if you do take a break, in other words, you take readings in the morning, right? Take a break. What are you going to do? You're going to recalibrate it before and after. In other words, put it back on the guy later. You're going to calibrate it before you do it. Okay, but on a practical basis, if it's not a ridiculously noisy environment and it's part of his 8-hour workday, his half-hour lunch break or coffee breaks, part of his 8-hour work break, I probably would leave it on. Because again, exposure, you're interested in what the exposure is over the 8 hours that he's actually working. Okay, so we know the relationship between excessive noise and hearing loss, right? But now we want to know, how are we going to protect the worker? He has excessive exposure to noise, and how are we going to protect them? Well, there's a whole series of methods that we can use, that we can implement to, just like any other kind of occupational exposure, to control exposure to a hazard in the workplace. Okay, so why implement them? Well, number one, it's required by OSHA, right? It's in the Federal Register. It's part of the Federal Register. There's a standard for it. Reduce compensation costs. Now, this is kind of, this is an occupational illness. A lot of people don't realize that they've had the hearing loss until after they've left the job, like years later, and so on and so forth. So it's a very difficult case for them to make. It doesn't show up so much in OSHA records, probably ridiculously underreported. So, and now people, because it causes stress, a lot of loud noise causes stress, you do get some absenteeism and injuries. You can't communicate, it's distracting, so it contributes to injuries as well. So how are we going to control this stuff, right? Okay, so a lot of times we just see 3 elements here, right? We see engineering. Well, in this case, engineering is broken down into 3. Engineering, administrative controls, and protective equipment. Usually the hierarchy we usually talk about. In this case, we're looking at engineering broken down into 3 categories. Number 1, eliminate the sound, eliminate the noise. Get rid of that device that's causing the problem. Number 2, substitute. Is there a machine that is less likely to cause noise? Causes less noise, does the same job, causes less noise, and so on and so forth. Number 3, engineering controls, right? In other words, you can't replace the machine. That's the only one you can use. You can't reduce the noise on the machine in order for it to work properly. Well, maybe you can put it into an enclosure, right? So is putting the machine into an enclosure the only way to protect the worker in that manner? I mean, what else could you do rather than put the machine in an enclosure that involves using an enclosure? What's that? Yeah, put it on springs, vibrate. Yeah, exactly. Put it on springs. You could do that. That's an engineering control. But I'm thinking about, I'm still going to use an enclosure, right? Put the worker in an enclosure, right? You guys ever been in a big power plant? Big power plant, you got all these generators and turbines and everything else that's enormously noisy. And where are the workers 90% of the time? They're monitoring it in a control room, in an insulated control room. So you can put the device in the noise source in an enclosure, or you can put the worker in an enclosure and protect them as well. So that's a control also. In fact, that's done more often than you would think. Okay, what about administrative controls? What do they mean, administrative controls? Training? Yeah, exactly. Training. What else? Yeah, what kind of policy? In other words, there's a machine makes a lot of noise. What kind of policy would protect the worker? Yeah. Yeah, forced breaks or change. In other words, he only works in that area for a short period of time. In other words, he trades jobs with someone else and nobody is exposed you minimize the exposure for each worker, by giving them other tasks that don't involve noise, right? So that's another way, yeah, that's another way you could use an administrative control, work rules, and so on and so forth. So, and then you get to what's the last line of protection? PPE, right. If you're an industrial hygienist and you're using PPE, what's happened? You failed. That's my personal attitude. You got to make a guy wear something to protect him. You failed, right? Because why have you failed, right? Which is the least reliable of all these things? Putting an enclosure, making him take breaks, and so on and so forth, which is the least reliable thing in this hierarchy. The PPE, because number one, it's got to fit right, it's got to work right, and most of all, what? He's got to wear the damn stuff, right? So that's the weakest point of this whole thing. You can make all sorts of rules and stuff like that. You can enforce the rules, make sure they follow them, and so on and so forth. You can put in engineering, you can do substitution, so on and so forth. But once you go to PPE, you're dependent on the worker to really comply, and you're dependent on the equipment to really protect them. And we're going to talk about like how we measure how effective these protective devices are protecting the workers, and applying something called noise reduction rating, NRR, noise reduction rating, in a second. Okay, but that's the word that you get the personal protective equipment. It's difficult at that point. Now I know if you're in Chernobyl and you're cleaning up radioactive waste, there's no getting around personal protective equipment, right? But anytime you can engineer it out or manage out the hazard. That's a much better way to approach it. Okay, noise controls. You have to have controls when the subject of sounds exceeding 90 decibels for a time-weighted 8-hour period. If they fail to reduce the sound levels below 90 decibels, hearing protection must be provided and used to reduce the sound level below the PEL. So you need to get the worker's exposure down below the PEL. And if it takes personal protective equipment, you need to use it. Okay, shift. And let's see, here's a kind of quick diagram. I've been having access problems on Blackboard. By tomorrow morning, I should be able to post again. So I'll get this PowerPoint posted on Blackboard. I know you don't have access to it right now, but I'll make sure that it's posted by tomorrow morning. Okay, so what are we doing here? We have enclosures, and enclosures, different kinds of materials, or vibration dampers, and so on and so forth. Different kinds of materials and substitution. We can retrofit products and applications, vibration dampening. And I used to have friends that were in a rock band back in the late 60s, early 70s. I loosely call it a rock band. They made a lot of noise, but I don't know how much rock they did. But at any rate, they would do their own recording. They had back in those days, reel-to-reel tape recorders and microphones and so on and so forth. And they had a room that they had set up, and they would record in that. They would do their own recordings in that room. So what did they need? They didn't need a lot of echo and stuff. They didn't want echo and stuff like that. They wanted to just produce the sound, get the sound recorded that they were producing. They didn't want a lot of reverberation and echo and so on and so forth. So what's the cheapest sound dampening material that you can think of that you could go out and buy? Egg crates. Yeah, they had egg crates. Staple up all of it. They went to the supermarket. They went to restaurants, collected egg crates, and they stapled them all up. So yeah, they used egg crates all over the roof, the ceiling, the walls, and so on and so forth. And then they found carpeting on the street for the floor. So people don't do that anymore. They're afraid of bed bugs now. So anything like that's cloth, nobody takes. I tried to throw out a couple of pillows, and the sanitation refused to take them. I put them in a plastic bag. They didn't want to touch them. And they were clean. It wasn't like they looked nasty or anything like that. Okay, so relocation of sources, routing of pneumatic or compressed air, discharge force from the outside of machine cabinets to the inside of machine cabinets rather than inside. So in other words, you got to clean them apart. You put it inside an enclosure. You bring the high pressure air nozzle inside and use it in there so you can capture the. So where are you guys exposed to high noise from high pressure nozzles? You guys ever exposed to noise from high pressure nozzles? Really loud too. I bet you get up about 100 decibels, maybe even higher. And I guarantee you in the past month, you've been exposed to this. Maybe, what's that? Maybe not car wash, but you got the right direction. How about those hand blowers? right? You push that button, how loud are they?
I stopped using those.
Right, they're pretty loud, right? They're pretty loud. And there's a lot of argument. That's pretty loud. Now I tell you what, do we have any in the school here? I don't think so. It's all paper towels in the school here, right? Too bad. Okay. I was going to say next week, if we have equipment available, maybe we could actually mention measurements. Or if when any of you guys wind up in the lab next semester, maybe you could do a survey of those machines and so on. There's a lot of issues with them, you know, in terms of whether or not the idea there is you don't use the paper towels, you save the resource of paper towels, and also you're not touching anything, so it's more it's more more sanitary, I guess. But you can also argue that it's blowing, you know, stuff off your hands, particularly off your hands. So maybe they're not more sanitary. Right? So who knows? Yeah, I'm sure the manufacturer doesn't want to know, so he's not doing any testing. Okay, so let's talk about what happens when you are exposed. Let's see what measurement it is. Okay, this is a graph that shows the level of noise that's produced by a machine that's operated at different speeds. So there's an engineering solution. If you have a drill that you operate, if you operate it at 3,000 RPM or something like that, it makes an enormous amount of noise. If it'll do the job at 2,000, if it'll adequately do the job you need it for at 1,500 RPM and reduce much less noise, there's a typical engineering control that you might use. Okay, substitute for the source. Using belts over gears, you know, writing from gears. So belts are required, flexible material. They're required using belt conveyors instead of rollers. You've seen the metal rollers so a lot of times you'll see them, you know, in supermarkets and stuff like that. And they can make quite a bit in a manufacturing facility. They use them to roll product around and stuff like that, and they make a lot of noise. So if they have a belt on, it's much quieter. Substituting metal or steel parts with materials that have high dampening properties, such as wood, nylon, stiff plastic, and so on. Using perforated or mesh panels instead of solid panels to help dampen sound. Okay, some substitution examples. If you've taken any indoor air quality courses or industrial ventilation, if you get into those courses, one of the issues is going to be noise. Noise generated by hoods, by exhaust hoods, by industrial ventilation systems, by air conditioning systems. Let me think, have I ever been in a situation where there was excessive noise from an air conditioning system that's been disturbing? Well, that's a design problem. Why is that so noisy? Why was there that noise? What's happening up there that made that so noisy? The velocity is too high, right? You know what? These diffusers that we don't have in this room. See these diffusers on the side here? They're taking the place of ceiling diffusers. Ceiling diffusers, the air comes down, and you'll notice that there are little curved vents in them. Comes down, so instead of going straight down and hitting you in the head, it kind of like they diffuse the air, they turn and curl, and the air mixes and so on and so forth. For most of them, you only have maybe each one only have a couple hundred CFM, cubic feet per minute coming out of them. This one over here, it seems like a couple of those are not working, right? Or they're blocked or are turned off. And these two up front here are taking all of that air that would go through these ones in the back, and they're blowing it in here. They're blowing it in here very fast, perhaps a lot faster than it's necessary. And back there's dampers that they can use to control the flow of air that's going through this ductwork, right? Now, it could be somebody left them wide open. It could be that they're motorized dampers or pneumatic dampers, and the controls, and they're connected to the thermostat back there, and the controls, that's called a variable air volume system. And those controls should control how open those dampers are. So if the room gets warm and we get more cold air, they open a little more, but not wide open, right? So it could be the controls are bad, could be the dampers are jammed, could be a number of reasons, but the reason for the noise was the velocity was too great. Same thing with an industrial ventilation system. The velocity has to be high enough that you want to capture the contaminant, keep it suspended in the air so you can get it out of the building. So if you're dealing with a gas or vapor, right? Well, that's not going to fall out inside the ductwork, so you can have a nice slow flow through the ductwork. If you're dealing with fine dust Well, now the air's got to move a little faster. Otherwise, the dust's going to settle outside the exhaust duct, right? The capture duct. So you need to get a little faster. If you're dealing with grinders that are spitting out large particles, you really have to keep the air moving really fast. Keep that stuff suspended so you can get it out of the space, right? So, but the deal there is that as you increase that velocity, there's more friction inside the ductwork, and you're going to generate more noise. Not only that, but when it gets to the end, when it comes out of the device, and it's got to go across the room to that other side, if you have a dead end up there in a right angle, 90-degree right angle, that air is going to blow up there, hit that ductwork, blow across, and make a lot of noise as it creates friction up there, right? Noise and heat, generating noise and heat as it hits that. If you had a gentle slope, gentle curve, the bigger the radius of the curve is, the less noise you're going to generate. So you can substitute. You see it here. You can substitute. You can modify the design of these air handling systems so that you can control how much noise they generate. Bad job here. I think it's got to be a control issue here, not a design issue. I would think they would have anticipated that noise. And it's not doing it now. Maybe they fixed it. So, okay. So here's some examples of modifying the process, the industrial process. So instead of dumping material directly into the middle of a hopper, it runs down the side of the hopper instead. Okay, and here they substituted a mesh belt guard for a solid one. So that helps attenuate the noise a bit as well. Relocation, move the equipment further apart or into areas where you can control it even better. Okay, we remember this formula. Okay, noise pathway. Okay, there's an enclosure. And let me see what else we have that's interesting here. Various kinds of materials for dampening sound. Ceiling tiles, baffles. Yeah, there you go. Okay, administrative controls. Rotating workers. We've discussed a lot of this stuff. This just came back. It's a repeat. Okay, hearing protection devices. Last option. Right? We failed. Haven't managed to control it. So now we fail. Now we have to provide the worker with a hearing protection device. Now, if you have a hearing conservation program because you're above 85 decibels, you need to provide that protection at no cost to the employee, and you got to replace it as it wears out or as necessary. Okay, types: earplugs, earmuffs, ear caps. Okay, earplugs are remarkably good at reducing the amount of sound that gets into the ear, but you got to make sure you have it installed correctly. It's got to be, compress it properly, get it into your ear, way into your ear canal, and have it expand so it really blocks out the noise. They're remarkably effective at reducing noise exposure. A little bit hard to measure. There's no techniques they can use it. Earmuffs are also very good. But what's the problem with earmuffs? Why would I have a problem wearing earmuffs and having them work effectively? Me personally. Glasses, right? If the earmuffs on, there's a route for the sound to get. They don't seal up quite as well. How about people with large sideburns or something like that, or facial hair? Same problem. We're in a business that doesn't like facial hair. What can I tell you about that? Too bad, right? Okay, so now let's take a look at a couple of these things. I brought a couple. Okay, so in this case, the earmuffs happen to be connected to this hard hat, pump cap, and let me find the numbers. Okay, there you go. See if you can't find a number on there, a model number. They buried in the model number. You would think they put a label on there, but they buried in the model number. I think if you look, it's on the outside, I think. Try the outside. All right, somewhere on there, there's a model number. Try on the earmuffs themselves. Rather than the hard hat, try the earmuffs. Yeah. Yeah, that's just a standard. But if you look on the outside of the earmuffs, somewhere on there, 26. Okay, what do you think that 26 is? That 26 is a noise reduction rating, right? Now, the paperwork that it came with probably had a lot more information on it, but they buried it in the model. That's a noise reduction rating. That means that that device is designed to attenuate the noise, so it reduces it by 26 decibels. Does it really reduce it by 26 decibels? No, it doesn't. It's not perfect, right? There's fit issues, there's use issues. It's not going to be used in a perfect environment. We discount that in a certain way to make sure that we assume a noise reduction rating for that thing that it really can achieve. Okay. Same thing with these with earplugs. And here, what do we got here? Earplugs. I think I got enough for everybody. You guys want to deal with these?
Bad memories.
You know, I had a guy, I used to have in my office, I had a box of these things. By the way, I don't want it back. Keep them, if there's any leftovers, keep them. Don't want that back. I did notice, I did come across at a conference, I came across an outfit that was creating earplugs, and what they were doing was they would literally, take you to a clinic where they would clean out your ear, shave, like go in and like clean all the wax out and take all the hairs out. If you ever get hearing aids, that's what they do. They clean out your ear completely, take all the wax out, clean all the hairs, everything. Just want bare skin. And they fit the earplugs, the hearing aid, to your ear. It's designed to fit specifically in your ear. That's why they cost $3,000. Or a pair of hearing aids, typically $5,000 and up, right? And they're not covered by Medicare or most insurance. Very expensive. Apple, Google, a whole bunch of other companies are starting to get into that market because they're dealing with a hearing device, like speakers and hearing devices that go into your ear. They're getting into that thing, getting into that market. And so you're starting to see just the tip of the iceberg in terms of large-scale manufacturer hearing aid devices. Also, the population's aging, so there's a market for this stuff. And they're starting to get into this market, or testing the market for this kind of stuff, and getting into things that have just as good performance at $500 or $1,000 or something like that. Difference is that for the most part they're kind of general fit. They're not specifically fitted to the individual, so they may not fit as well. You may have to do your own judgment on how they fit. They may have to come with multiple different, housings or something like that. Just like little, your ear pods a lot of times come with that. But they're getting into this market, so they would literally, in these hard type, the best kind would be ones that are designed specifically for your ear, and they can take a mold of your ear and do that. This one outfit I saw, they actually used scanning technology after you cleaned out your ear to model the inside of your ear canal. And they would produce a plastic earplug that would go into your ear just like that and fit perfectly. And it even had a little bit of electronic. They used 3D printing for it. They used a little bit of electronics in there, had a little tiny microphone. So it could actually do active noise reduction, like Bose headphones, in these little earplugs as well. And so it's a blocker, and it's also active noise reduction. Maybe we'll get a chance, we'll talk about that at some point. So here you go. And you can see custom fit earplugs that are designed specifically for a person's ear. Okay, and then we went through foaming, and they were, oh look, same video. Okay, so fit testing. How do you test whether or not this is really effective? For the most part, you're not going to see much fit testing done with these kind of devices. The assumption is that if you get them to fit properly, you assume what the noise reduction rating, you assume how protective they are based on the manufacturer's noise reduction rating. But it's not the same thing as taking these headphones and putting on somebody's head, producing a noise, and then measuring the level of sound inside the headphones and outside the headphones. Very similar, you guys may have seen respiratory fit protection, where they do that, right? Like mask, and you sample the air inside the mask and outside the mask and compare them. So you actually can test that, do a quantitative test. They can do that with these things as well. Most situations they don't. They rely on the noise reduction rating. Since you're not really testing how good they are in a particular individual, you have to discount the noise reduction rating. So you don't. So you can be positive that you get a minimum amount of noise reduction, even if they aren't quite perfectly fit. Okay. So, and the frequency response, depending on the type of device you're using, it might have a better response at reducing sound levels at different frequencies. Again, Octave band analyzer, I hope you figure out whether the device you're using for detecting the worker is really appropriate for the kind of sound, the frequency of the sound that you're exposing them to. Okay. Selection and protection, or sound level, work environment, how often they expose to excessive noise, how durable does the device have to be? And when you have them on the job, if you have these things on, he's still going to be able to safely do his work. Okay, noise reduction rating. Okay, usually they'll have a tag like that either on the packaging or the device itself. It didn't say anything on the plastic packaging for these, right? It was on the box. You know, if you saw the box that they came in, that would be on there. Okay, and I think this might be typically, looks like it could be earplugs, box of earplugs. In fact, the noise is on the earplug package. Okay, so 29 noise reduction rating of 29. Well, what does that mean? Okay, OSHA requires that the noise reduction rating be adjusted prior to job site evaluation. Okay, field attenuation, in other words, that's the level of exposure to the worker, the assumed level of exposure to the worker. Well, what's it equal to? It's equal to that. That's how much of the attenuation is, how many decibels you've reduced the noise. It's equal to the noise reduction rating minus 7. Okay, so if our earplugs were 29, minus 7 is what? 22, right? Then we divide that by 2. We're down. Now we have 11. So the field attenuation, the amount of decibels you've reduced the sound, is 11 decibels. Right? Okay. So noise reduction rate of pair of earmuffs is 30 decibels. If the sound pressure level on the plant is 97 decibels, will this provide adequate protection according to OSHA or according to ACCIH, which is the same as the NIOSH, I believe. Okay, so what would be the functional field attenuation amount of decibels would reduce the sound for a pair of earmuffs that is a noise reduction? So 30 minus 7, right? 23 divided by 2, 11 and a half. We're starting at 97. What are you down to? That's 85 and a half, right? That's right, 85 and a half, right? So is that enough? It is, right? If you use NIOSH, if you use OSHA, right, that's enough. You just got to get below 90, right? What about if you use the ACCIH or NIOSH standard, recommended exposure limit? No, you got to get to 85, right? It's not enough, right? So you need more noise reduction than the earmuffs, these particular set of earmuffs, will provide in that environment. What can you do about that? You got to throw those away and get another pair? Is there another solution other than throwing them away? The earmuffs, they're expensive. They came with a hard hat. They cost money, right? They like them. You know, they're pretty. They have, you know, like New York Jets, New York Giants. They got versions of them, right? The worker wants to use, he likes them. He thinks they're cool. He wants to use them. Do we have to throw them away and get something else? How about if we combine them? In other words, is there anything wrong with wearing earplugs with the earmuffs? Right? You can actually combine the noise reduction rating for those two devices. Okay, noise reduction pair of earmuffs is 30 decibels. With respect to doesn't quite. Yes.
The 7 and the 2.
Yeah, that's the OSHA specifies that. Why 7 and 2?
Why come with the calculation anyway? Why can't they just be the actual number?
Because number one, because you're not fit testing. In other words, in order to get that noise, remember they determined that noise reduction rating of 29 in a laboratory, right? They take a soccer ball that was Pele kicked it once and sat autographed. They take a soccer ball, they put the headphones over it, they put a microphone inside the headphones, and they get it so it's perfectly fit, perfectly tight, pressed up against that soccer ball, not really a soccer ball, but a fake head, right? A fake head. And then going to measure the sound outside of the headphones and earmuffs and inside of the earmuffs, right? And the reduction is 29 decibels, right? But that's perfect fit. That's not a human head, that's on a simulator, that's in a laboratory. So now, if I could put them on your head and do the same measurement, I would know exactly how good those are with your sideburns, your facial hair, your face shape. I would know exactly how good they are at reducing the sound level inside your ear, right? I would know what it is. I wouldn't have to guess. I wouldn't need that to tell me noise reduction rate. That's cumbersome to do, right? So instead, they give you what the laboratory rating is, a perfect situation, not fitted to a specific person, preferably sealed up. And OSHA says, well, yeah, it's perfectly okay. You can do that, but you can't use that number 29. You have to adjust that number to this using this formula, and then you can be pretty much certain that you can deliver 11.5 decibel reduction, right? Even though it says 29, you can pretty much, on anybody that is reasonably well fit with these things, deliver an actual 11.5 decibels. Okay, that's not my judgment, that's OSHA. Right?
Both
Yeah.
numbers, shouldn't one number be a variable then, if it's not all the same for everyone?
Well, that's the point. In other words, you can't predict. I mean, you have a narrow face, somebody else has a round face. Who's going to work? Should we use, instead of 7, should we use 5 on your face and 9 on his face? No way for us to tell. So they take the safe route. They're looking at worst case scenarios, right? In other words, universal worker, we're going to use this number. We're going to subtract 7, divide by 2, and we're going to use that number universally for everybody. A lot of people, it may perform better. Right? In fact, I would hazard a guess, for most people, it will perform better. For 80% or 95% of people, you get better than 11.5 decibels. But for some small portion, you won't. You'll get either 11.5 or maybe even a little less, right? Because it's just the fit or whatever it is. It's just not working as well for them. And OSHA's been, I'm sure they've done research on this, and they figure, you guys take statistics? Have you guys taken statistics? How many of you guys have taken statistics? Right? You talk about confidence interval, right? That basically you want to know confidence, and you want that 95% certainty that you're going to protect 95% of the workers at the level that you think you are, right? If there was really going to be 100%, right? Well, then you take this noise reduction rating at 29 and say it's 1 decibel, right? Which is ridiculous, because then they wouldn't even be worth wearing, right? You wouldn't be able to assume any reduction. So this is a formula they've calculated would protect the majority of workers at that level, at 11.5 decibel reduction, right? Yes.
Are there any examples of workers using noise canceling technology in the workplace?
Yeah, I'm sure they do. I'm not, but I don't think OSHA, I don't think OSHA's really caught up to that yet. So I'm not sure that there's any that are certified this way or have a noise reduction rating that you can apply to OSHA. If you guys find out different, let me know. I have never seen, like Bose headphones, they don't come with a noise reduction rating on the outside of them, and also they're designed for, certain kinds, they're designed for general use. I know I've used them, and like in a room with conversation, they don't reduce the noise that much. But on an airplane with that constant buzz of the engine, it almost completely erases it, right? So they're designed for environments where, we're in a car or something like that, a moving vehicle, or something like that. They really seem to work pretty well. But in other environments, they don't seem to work that well. And you saw that graph that showed that those earmuffs at low frequencies, they don't really attenuate much, but at higher frequencies, they attenuate quite a bit. Okay, proper use. Okay, and you don't want them removing them. You want them to keep them on, right? Exactly. This is, if you guys, tomorrow is the 18th anniversary of 9/11, right? So there's been a lot of pictures, like on Facebook, I've seen a lot of photographs and pictures from post the weeks or months after 9/11 and the workers and so on and so forth. And I can't tell you how many pictures I see. A lot of us went down there and did fit testing, helped them with fit testing and stuff like that, and gear and stuff for the workers that were doing the cleanup and especially after the immediate disaster. You know, there was a recovery operation for a couple of weeks. They thought they might be able to recover some people. Unfortunately, they weren't. But so they were working on the pile very vigorously, trying to see if they could rescue anyone. And so a lot of the firemen, you look at the pictures back then, a lot of the firemen, nobody's wearing. They're wearing their respirators, they're using dust masks, and, you know, most of them, they got them on their heads and stuff like that. They were desperate to get through, you know, like see if they could rescue somebody. For the first couple of weeks, no one was using protective gear. You know, and that, you know, there's all of that concrete dust, and which is highly alkaline and abrasive, and probably full of silica and asbestos and everything else. And there's the fumes from the burning plastics and stuff. So when you look back at those pictures, you'll see that especially early on, especially in the first few weeks, first month, that a lot of the first responders, a lot of the people went down to work on the pile. We're not wearing protective equipment at all. If they were, they'd only be able to wear it. It's still pretty warm. It's still September, right? So there were warm days. It's tough to wear that stuff when it's hot. And it was hard to spend a lot of time, you know, using those things. And they would clog up quickly, right? A lot of them were particulate filters, and there was so much dust in the air that they would clog quickly. So basically, you couldn't wear them, you couldn't breathe through them anymore. Okay, so hearing protection, not hearing protection. Hearing aids do not block out enough sound for most workplace noise. So hearing aids not going to help you. Okay, some hearing aids can actually increase the noise level at the ear. They're basically just amplifiers. A microphone on the outside, they amplify the sound. They preferentially might amplify the sound. What frequencies do you think that they amplify the most? Right? If you have a hearing aid, you want to be able to talk with people. So it's in the range of, you know, vocal communication, maybe 400 hertz to 4,000 hertz or something like that. So that's where they work the best. They amplify the sound the most. You don't want noise amplified, so they work specifically in that range. Yes.
I have a question about that. So, is there any selectivity in hearing protection in general? And I'm thinking about like having a construction worker wear hearing protection and not being able to hear an alarm or a car,
Right.
truck backing
Yeah.
up.
Yeah.
You know, like is there an octave band?
Yeah, that's a good question. I don't think so. For like warning signals and stuff like that, or sounds like that, I don't think so. But they definitely, each different kind of device has its own signature in terms of like what octave, what frequencies it will reduce, attenuate the most. Like this is, we're looking at earmuffs, and you can see that down at 125, 250 hertz, right? They're not attenuating the sound as much as they are in the rest of the band. Right? They're not as good as filtering out low frequency sound as higher frequency sound. But other devices may be better at that. You know, maybe plugs are better at that than the earmuffs are.
So recently at work, we've been using this new vendor. I don't recall the name. They're doing custom fit earplugs.
Oh, no
And
kidding.
they claim that they only block out the unwanted noise.
Yeah.
They
Did they give you a noise reduction rating with them?
They did. I don't remember the
Yeah.
brand name.
Look it up. But look it up, because it's all about fit. Fit's important. He emphasized how it was so important to get that rolled up, make no creases in it, or get it as high as you can, put it as deep in, put it
They do
in the right.
custom fit.
Yeah, those
They
custom
do
fit, yeah.
models,
Yeah, like I said, this other outfit, they actually printed 3D. They would use an optical device, scan the inside of your ear, and then they would 3D print earplugs that would fit your ear canal perfectly.
So that they clean out your ear.
Yeah, did they clean out your ear?
No, I think with the mold in there.
Yeah, oh, they put a mold device, okay, yeah. Right, so some sort of plastic material that, okay.
They did it for a while.
Yeah, and then pull it, yeah. Yeah, okay, well, that's reasonable. Would have been nice to clean out your ear, right, shave out all they do. If you go for a hearing aid, that's exactly what they do, to clean your. Anybody watch CBS Sunday Morning, ever? They just had, I'm trying to think of the name. He used to be the technology editor for New York Times. Tall, skinny guy. And he went and got fitted for a hearing aid. The part of this story was about they did a story on hearing aids, how expensive they were, how the technology is changing, and they used a camera to go in there and clean out all the hair and the earwax and so on and so forth before they put the mold in to create the hearing aid. They do that for hearing aid. That's why you spend $5,000 on hearing aid. And then they do audiometric tests in a booth to make sure that like it fits right, it's responding correctly, and that the particular device is tuned for the frequencies that you've lost and so on. So it's not just a matter of just giving anybody one of these. But on the other hand, that means making a $5,000 or $6,000 means that 90% of people that need a hearing aid, they don't got one. Period. They don't have a bad hearing aid. They don't have a not very good hearing aid. They don't have a sort of good hearing aid. They have no hearing aid, right? Because it's just they can't afford $6,000. And who needs them? Usually, people that have done worked in noisy environments, probably not high-wage labor and stuff like that. And since they're not covered by Medicaid, Medicare or Medicaid, then they just don't wind up getting them. Okay. Now, hearing loss is supposed to be reported on the OSHA 300 log. Does it show up all the time on the OSHA 300 log? Probably not, because what happens when does a guy realize that he has significant hearing loss, right? After he retired, right? Or when he's gone to another job 10 years later or something like that, right? So it's not the kind of, and in general, occupational illnesses are underreported compared to injuries. Injuries are obvious. You fall, you break an arm, you're out for a week, and stuff like that. So those are obvious. Those get reported pretty reliably. Fatalities, then don't miss a fatality. So they're 100%, don't miss any of those. But occupational illnesses, things like hearing loss, are definitely underreported. Okay, so let me see what we can close out with. Okay, so here's a sound contour. We're talking about mapping out sound. These are sound contours. So with a sound level meter, they've gone around and they measured where is 94 decibels. So 94 is here, 94, I read 94 in all these spots along this line. So you can actually predict that as you walk through here, this is like, I'm making numbers, this is 90 decibels, and then as you cross this line, it's 94 decibels, 96 decibels, 100 decibels, so on and so forth. So use that to map out contour lines.